Hello everyone. So previously we had discussed on the this one Fenwick tree algorithm. So today we'll be discussing on the topic heavy light decomposition algorithm. Right. So let's get into the definition part here. So what does the definition part say here? Heavy light decomposition (HLD) is a technique used on the trees to decompose them into the chains. Again, heavy light decomposition is a technique used on the trees to decompose them into the chains, nothing but the paths, such that queries along any path between two nodes such that queries along any path between two nodes can be efficiently answered using the segment trees or the Fenwick trees. Right. Again, heavy light decomposition is used with the segment tree or the Fenwick trees. Right. So just remember this one. Many a times for the intense optimization or the this one extreme optimization, we'll be going with the heavy light decomposition within the segment tree or the Fenwick tree. Right. So we have solved this one heavy light decomposition when we were solving the segment tree or the Fenwick tree. This one within the segment tree, Fenwick tree, and the sparse table playlist. So we have solved some problems that involves a heavy light decomposition algo, right? So that is what it is, right? So basically we are just discussing on the same now, right? So heavy light decomposition HLD is a technique used on the trees to decompose them into the chains or the paths such that queries along any path between two nodes can be efficiently answered using the segment trees or the Fenwick trees. So now we have the idea on the segment tree and the Fenwick tree algorithm, right? So we went with some 2 or 3 algorithms in the segment tree, main segment tree, normal segment tree, and the persistent segment tree, along with the lazy propagation in the segment tree. And also previously we had went through the this one Fenwick tree algorithm as well. Now how does it help? Basically it helps convert the tree path queries into the array range queries in the logarithmic time and logarithmic time. Just remember this one. This is very important one. Now let's get into the explanation part. Let's get into the explanation part, right? So now in a tree queries like find maximum value between the node U and the node V, or update value at the node X, right? So whether we are going with a min max or the update value at the node X are or difficult. Basically they are difficult because there is no direct linear structure for it, right? So there is no this one difficult because there is no direct linear structure for it. So this is one of the important points I found to explain here. So in a tree, queries like find max value between the node U and node V or update the value at the node X are difficult because there is no direct linear structure for this, right? So HLD or the heavy light decomposition algo solves this by breaking the tree into the heavy and light edges. So what it does, HLD, basically heavy light decomposition algo, this breaks the tree into heavy and light edges. So that's what it does. So this is very important. For each node, the heavy edge this one connects it to its child with the largest subtree size. For each node, again, the heavy edge, we now have the heavy and the light edges, right? So heavy edge, what it does, it connects it to its child with the largest subtree size, right? So what does this one light edges do? All other edges are except that one, this one, except the connected ones. All other edges are the this one light edges. Just remember this one. This is important. Each heavy path or the chain can be represented as continuous segment in an array. So this can be represented as a continuous segment in the array, allowing the segment trees or the Fenwick tree to work efficiently. Again, each heavy path chain can be represented as a continuous segment in the array, allowing segment tree or the Fenwick tree to work efficiently. So any path between the two nodes crosses two nodes crosses at most peak of logarithmic and light edges. See, this is very important, right? It enables the fast queries as well, right? Thus any path between two nodes crosses at most big of log and light edges, enabling the fast queries. So some of the example problems are here. So we will build a tree of n nodes. We will be building a tree of n nodes, right? So we can make use of the heavy light decomposition to flatten the tree. Then there also we can make use of the heavy light decomposition. The final one is we have to perform a sum query on the path between two nodes. We have to perform when we need to perform this one sum query on the path between two nodes, basically, right? So let's do one thing. Now, this is the problem we'll be going with basically. So we'll build a tree of n nodes first. Then we'll be making use of the heavy light decomposition to flatten the tree. Then we'll perform the sum query on the path between the two nodes, right? So that's what we'll be doing. Let's see the same thing actually, right? Let's start writing the code, or let's start implementing whatever we discussed in the explanation. Let's try to articulate that one in the form of code. Now, yeah, just give me a second here. 1 second. So let's go with a heavy light decomposition example, right? So first thing is we'll be going with a query. Query is nothing but we have to find the sum of the values on the path between two nodes. So that's what we'll be doing, right? So first step would be let's build the adjacency list for the tree. So I'll be considering 7 here. Adjacency ADJ, I'll be going with this one. Sorry, this is not taking it all. N equals 7. This is fine. Adjacency. So this one will be 1 second. I'll just make use of the for here. For we have to use something, right? I'll just go with the underscore for this one. Range, I'll just go with n plus 1. So this is fine. Next step, let me consider the edges here. Let me go with 1 comma 2. Also, let me go with 1 comma 3 as well. And let me go with 2 comma 4 and 2 comma 5 and this one 3 comma 6 and 3 comma 7. So 3 comma 7, this has to be, it is taking like this. Yep. We write this one within the parenthesis, right? So I can just write it on this way. Let me show you the build here. So this one 1 to 2 actually, and 1 to 3 as well, right? 2 to 4 and 2 to 5 here, right? So 3 to 6 here and 3 to 7, right? So this is the build if you draw the tree, right? So this will be 1 2 3 4 5 6 7, the simple example I am going with actually, right? So this is the edges I have represented, this one edges basically 1 2 3 4 5 6 7, right? So let me go with the this one for loop. So this one will be for u comma v in edges, for u comma v in edges. So I'll just go with ATJ of u. So we have to append v here in this case. This one has to be in the parenthesis, right? So this is fine. Also ADJ of v. So let's go with append u. This is fine. Yep. Now the next step would be so we have to initialize the arrays. So let me go with the parent equals, we have to initialize the arrays, right? So this one I'll just go with 0 into n plus 1, right? So let me go with the depth as well here. Depth is I'll just go with 0 into again n plus 1, right? So I'll just go with size equals again 0 into this one, what do you call, n plus 1. Finally, let me go with the heavy variable heavy here. This one will be minus 1 into n plus 1. So this is fine. Yep. Now let's move on with the next step, or the step 3. First step we went with building the adjacency list for the tree, right? So I show you the build basically the tree. So this one is the first step. The second step, this one, whatever we have done, we are just initializing the arrays here. Let's move on with the third step. In the third step, what we'll be doing, let's go with the DFS to compute the size in heavy child, right? So here I'll just go with def DFS of parameters u comma v. First step, let me write this one quickly. So this one will be parent of u. We are performing DFS, right? Well, it's p, and let's go with the size. We have already went with the initialization size of u. Let me go with 1. Also, let me go with a max size here. max size, let me initialize this one to 0. This is fine. Let's make use of the for loop. So this one will be for v in edge, for v in not the edge man, for v in adjacency, right, of u basically, right? So this is fine. So within this for loop, let me go with a simple if condition. If v not equal to p, then what I'll do, let me go with depth, not the def, depth of v. Let me assign this one to the depth of this one, depth of u plus 1. This is fine. And let's recurse now dfs of v comma u. This is also fine. And let me go with size of u, this one, size of u equals size of u plus size of v. This is fine. The next step would be if size of this one v, if it is greater than max size, so we have already made use of max size, then if size of v is greater than the max size, then we have to assign the max size to size of v, right? Updating basically. Max size equals size of v. This is simple man. EFS. Finally, heavy of u, this one, let me assign this one to the v, right? So we are done with performing the DFS. Now let's do one thing. Let me call the DFS function here, DFS of 1 comma 0 initially. This is fine. We are done with the this one. We have successfully performed the DFS just to compute the size and the heavy child. So in the explanation, first we have to compute the heavy child, right? All the other this one edges are considered as light, right? So that's what we discussed earlier. So we have went with the DFS to compute the size and heavy child. This is fine. Now let's do one thing. Let's move on with the step 4. Nothing but we have to decompose into the chains, right? So we have to decompose into the chains. So this one, let's we go with head, that is equal to 0 into n plus 1 basically, right? 0 into n plus 1. Position equals, so this one will be 0 into again n plus 1 itself. Now let me go with the current position. So this one will be current position equals, let me initialize this one to the 0. Also let me go with the value that is equivalent to 0, 3, 2, 1. Let me go with certain values. 10 is fine. Let me go with 5, 7, 6, something like that. This is fine. These are the node values. These are the node values again, right? So this is one indexed again. This is one index. Don't get confused. This is not 0 index. This is one index, right? So this is fine. So now let's do one thing. Let's go with a decomposition. I'll just name this one decompose, right? So this one, I need u and h as parameters, I believe. So let's see, u and h. This is fine. So let me go with global. So this one is current position. So this is fine. Now head of u, let me assign this one to the h. And the next part is, let me go with position of u. Let me assign this one to the current position. And current position equals current position plus 1 here. Finally, let's write the simple if condition here. What if the heavy of u that we have considered right earlier? So this one, if it is not equal to minus 1, then I'll just go with the decompose. We are just recursing here. Let me go with heavy of u comma h. This is fine. Let's go with a simple for loop man. So this one for v in adj is a variable adjacency, right? So this one of u within the for loop, if v not equal to parent of u, then and v not equal to heavy of u, this is fine. Then what we'll do, let's go with the decompose of v comma v, right? So this is fine. Now let me call the decompose here. Decompose of 1 comma 1. This is fine, man. We went with the decompose help function or the helper method, man. So let's go with the fifth step. Nothing but let's build the segment tree for the values, right? So this one, let me go with the tree equals 0 into. So this will be 4 into n. This is fine. Let me go with the base equals 0 into n. So we are just building the segment tree for the values from here. Again, don't get confused here. So this is fine. Done. So let me go with the for loop here for I in range. For I in range. So this one will be 1 comma n plus 1 index, right? So this is fine. Now let me go with a base here. Base of basically iterated value of the position. So this one we have to assign this one to the values of I. Iterated value of the iterated value of the I. Iterated value of the values, sorry. Now, as I have said, we have to build a segment tree for the values. Same thing, we have to go with build, and we have to go with a query, as well as we have to go with a path query. These are the three methods that we'll be going with. What you want me to do? Let me type or let me copy paste. Let me type, man. So anyways, so next we'll be going with this one, basically centroid or this one, those kind of things. So we'll be leaving the segment tree and this one behind. Anyways, let's do one thing. Let's build the segment tree for the values. Now let's go with the build actually. Let me type. I'll just go with the build. I need the parameters index left and right. So within the build, same thing. If L equals R, then if left equals right, then tree of index. So let me go with the base of L, right? So else what we need to do? Else, so let me go with mid equals left plus right by 2. So this is fine. Now let's recurse. We are building, right? So I'll just go with the build here. So for the left one, index, left subtree, index into 2, left, as well as this one, mid basically. Mid. Yep. Don't forget that the segment tree is a binary tree, right? So we are going with the mid. Why we have to go with this? These kind of questions should not arise, right? So this is simple. We have solved a hell amount of problems, and we have seen the algorithm. We have implemented so many things within the segment tree. We know the heavy light decomposition. We'll be knowing this one as well. Even the centroid ones, calculating the centroid, that will be discussing that algorithm. We have done that one with the DP as well. So many things at this point of time, you shouldn't those kind of doubts has to be clear basically. So now for the right subtree, let's recurse. I'll just go with the build here. Build index into 2. Oh, this one for the right subtree, right? 2 plus 1 basically. Mid plus 1. Then we have to consider right. This is fine. Now let me go with tree of index. Let me assign this one to the, sorry, not try, tree of index into 2, tree of index into 2 plus tree of this one, index into 2 plus 1 basically. This is fine. Now let's do one thing. Let me call the build function here. So this one will be 1 comma 0 up to n minus 1, right? So this is fine. We are done with the build, what do we call, build helper method, build function basically. So let me give def here. So this would have caused the indentation issue. This is fine. Now let's do one thing. So we are done with the build function. Next, let's move on with the query function. So I'll just go with a query here. So this will be index comma left comma right. So query left comma query right. So this is fine. 1 second. One second. So let's continue with the query. So I'll just come here. Same thing. If the query left, sorry, query right, we have to consider, right? If the QR is less than left or query left, so this one greater than right, so then in that case we have to return 0, right? So this we know. Next, if query left is less than or equal to L and right less than or equal to query right, then what we need to do here, then we have to return this one, 3 of index. So this is fine. Now let's do one thing. I'll just go with the mid equals left plus right by 2, right? This is fine. We are just calculating the mid. So I'll just go with the return here. So this one has to be query. This is fine. Mm, one. Go with left as well as the right, right? So for the left, we'll be going with the index into 2, comma left, comma mid, also query left and query right. So this is fine. Also, we have to include this one. What do you call? Right subtree. So this one will be query again. We are just recursing here, right? So this one will be index into one has to be x1 index. Okay, 2 plus 1 right side, so 2 plus 1 again we have to go with the mid plus 1, so this one will be right, query left and query right. So we are done with the query, this one query function. Now we are left with only one thing, that is nothing but we have to query the path using query the path sum using this one, heavy light decomposition. Nothing but let's name this one, this function as the path query man, right? So I'll just go with the def. So let me go with path underscore query. So this will be u comma v. Let's consider u and v as parameters. So result, let me assign this one to the 0. Let me go with a while loop here. While head of u is not equal to the head of v, we have to consider, I believe, right? Yep. This is fine. If what if the depth of this one, head of u, we have to consider of head of u is less than, basically I'll just give depth here, depth of head of sorry, head of v. Basically what if it is less, then what we need to do, so let's assign u comma v to v comma u respectively, right? So we are done with this part. Now what we need to do, we have to go with the result equals result plus again let's make use of the query. We have already written the query helper function, so I'll just go with 1 comma 0. So this one will be n minus 1 position of let me go with the head of u. This is fine. Head of u is fine. Also we have to go with the position of u as well, right? So this is fine. Yeah, position of. Now let's assign u to parent of head of u. So this one is parent of head of u. This is fine. Now let's write the simple if condition. If what if the depth of u is greater than the depth of v, right? So this one depth of u, what if the depth of u is greater than depth of v, right? So this is fine. Next step would be again u comma v. Let's assign this one to v comma u respectively. Now let's go with the again let me go with the result equals result plus one query of, let me give you a 1 comma 0 to n minus 1 basically. Yep, this is fine, and we have to include position of u along with the position of v. Yep, we are done with this part. Finally we have to return the result, right? So we have to return the result. So did I do something wrong here? While loop, this is fine. while I have considered, oh, if depth of view, this one cannot be within the while loop, man. So this one has to be outside. Right, so this is fine. Mm, this vector, 1 second. So yeah, this is fine. Let me move the result here. Also this one result return. We have to return the result, right? Return the result. Yeah. I was thinking that something was wrong. The indentation was wrong, basically. This is fine. Now we are done with the algorithm. The last step is let's go with a example query. Let's go with a example query. So I'll just come here. Let me print something for the interactive purpose so that we understand this one clearly with the example. So I'll just go with some between node 4 and 7. So this is fine. So let me call the path query here, right? Path query of what we have considered 4 and 7. Sum between the node 4 and 7. We are calculating basically, right? So this is fine. For before moving on with the output part or before moving on with running the code, let me explain whatever we have done here. Right? So this one, see, first part is we went with a build here, right? So this DFS is fine. Uh, Decompose DFS, I have explained this one. So see here, this one has to be multiplication symbol. So many times I do this mistake, man. Uh, Initially we went with a build DFS, then the decompose help of this one, then we went with the building the segment tree basically, right? So this build, so we are just building the tree, right? From we have 7 nodes basically. So this one I had showed earlier, 1 to 7, 1 2 3, then 4 5 6 7, right? So we have 1 to 7, basically 7 nodes using the adjacency list, right? So then we are computing the, so we went with the DFS. See here, DFS, where is DFS? DFS helper function. So what it does, it computes the size of view of each subtree and it identifies the heavy child. It identifies what it does. It identifies the heavy child. See here, heavy of u equals v finally. It, what it does, again I'm telling, DFS computes the size of u of each subtree and it identifies the heavy child. So then what does decompose do here? We have made use of the decompose function as well. What the heck does this one decompose do here? So this one maps, it maps the each node to its position in a linear array based on the chain decomposition, right? So this one, whatever I have written here, decompose helper function. So this one maps each node to its position in a linear array based on the chain decomposition, right? So now let's come to this one, build part, this one, right? So build method or the build function, basically. Build function, this builds a segment tree over this flattened array. This builds the segment tree over the flattened array. Now this one, whatever we have written here, path query, this helper function, this function basically, this implements the path query of u comma v, which moves up the chains until both the nodes share the same head, right? So it moves up the chains until both the nodes u and v share the same head, right? So it performs the segment tree range queries along the way. It performs the range, this one, segment tree range queries along the way. Just remember this one. This is very important. Finally, this one, query path between, we are going with a query path between the nodes 4 and node 7. This one, right? So when I run the code, what is the output that I need to get here? This one basically 29 I need to get. Why I need to get 29? So let me show you. So let me write this one. So this one is 1 2 3. This one I had already written. Let me write this one again. 1 2 3 4 5. So this is fine. Finally this one 6 and 7. So this is fine. So before writing this one, let me remove this one for a second. So see here, values we have been given 0, 3, 2, 1, 10. This one 5, 7, 6, right? So now let me show you this one correctly. So this one edges we have considered 1, 2, 1 to 3, 2 to 4, and 2 to 5 basically. The simple one we have considered, right? And 3 to 6 and 3 to 7. These are the edges basically, right? So value we have here basically 1, 0, 3 to 110, Uh, 5, this one 7 and 6, right? So this is fine one. And again, node values are one indexed here. Node values are one indexed, right? Again, don't this one, this starts with the index 1. This is again index 1, 2, 3, 4, 5, sorry 5, we have 6. After 5 we have 7. Don't get confused here. 7 and 6, basically 7 and 8, index 7 and 8. So this we have, let me write this one, value 7 and 6 we have at the end after 5. Don't get confused here, right? So this is fine. Now what we are doing basically here, um, we are going from this one. We are considering path from 4 to 7. Path from 4 to 7 means here, see, we can just go from 4, 4 to 2, from 2 to 1, then 1 to 3, then finally from this one, 3 to 7. So this is the path. 4 to 1, 3, 7. So this will be the path from 4 to 7. 4, 2, 1, finally 3, and finally this is 7. Sorry, finally 7. 4 to 1, 3, 7. From here to here, 4 to 2, 2 to 1, 1 to 3, and 3 to 7. So this is the path. So what is the value we have? So see here, we have the values. I'll just write it over here. 0, 3, 2, 1, 10, this one 1, 10, 5, finally 6, and this one 7 and 6, right? So this is one index, right? So this is mapped to 1, this is mapped to 2, this is mapped to 3, this is mapped to 4, this is mapped to 5, this one to 6, and this one to 7, and this one to 8. This is fine. Now we are going with the what do we call, this one, uh, uh, what do we call, we are considering from the path 4 to 7. So now we have to go with this path 4 to 2, 2 to 1, 1 to 3, and 3 to 7. So 4, for the 4 we have the value, this one, what do we call, for the fourth one we have the value, sorry, this one I think this will start from the zeroth index itself, this one. So this one, this has to be 0, 1, 2. This one I got confused, man. Sorry. This one has to be 3. Let me do one thing. Yeah. Yep. Let me do one thing. So this one is 4. Let me change this one over here itself. This one is 5, and this one is 6. And finally, this is not 8. This is 7. Right. This indexing start from the 0 itself. So this one here, what we will be doing. So we have to consider the index 4. Right. Index from index 4 to index this one. Index 4 to 4 to 1, 3, 7. Right. 4 consists of the value. See here, index 4. This one 0, 1, 2. 0, 1, 2, 3, 4. 4 consists of the value 10. So this one is 10. So then 2 we have. Node 2 consists of the value 2 itself. So this one plus 2. So then the node 1 consists of this one 3. So this one is 3, right? So then the node 3, we have the node 3. So 3 consists of the value 1. So this one is 2, 10 plus 2 plus 3 plus 1. Finally, we have this one. What do we call? 7, right? 7 consists of the value 6 plus 6. So this one will be 10 plus 2 plus 3. 10 plus 2 plus 3, 15. 15 plus 1, 16. 16 plus 6 is 22 here. So we have got the output 22 here. So we need to get the output 22 accordingly with that, this one. What do we call? The example that we considered here, values we have considered here, right? This one, right? So the output that we need to get here is 22 basically. Let's check whether we get the value 22 or not. So just give me a second here. Yep, let's try running the code. I hope this works, man. Let's see. I'll just give here Control J. So let me give here Python heavy light decomposition algo name dot file name dot py. So we have the error here. Tuple object is not callable. Just one to line number 33. What mistake I have done here? Line number 33. Oh yeah, I have forgot to mention the comma here. This is fine. Again, let me give comma correctly here. Else we'll get the error. So this is the only error. Let me run this one again. Yeah, so now we are getting the sum between the node 4 and node 7 as 22. So that I have showed, just now I showed, right? So we are getting the desired output. We are getting the desired output. I have explained you every single, this one, what do we call, single function that we have written. Initially, this one, and this one example that we have considered, edges we have considered, and now we performed the DFS, then we went with the decomposition, then we went with a segment tree, right? So build of the segment tree, then we went with a query along with a path query where we get the result basically, right? Where we perform this one, what do we call, heavy light decomposition within the path query, right? So now we are getting the desired output. This is it for the heavy light decomposition. This is very simple, right? So I have considered, or I had considered this one. I have considered this one very simple example, right? I have shown you step by step. I hope this is completely clear, man. We have went with a heavy light decomposition. We have got the desired output. This is fine. Now, next what we will be doing, so this is it for the heavy light decomposition algorithm, right? So this we can either make use of it within the segment tree or the Fenwick tree. You can just try to do the same thing with the Fenwick tree as well. This is one of the very important algorithms. So this one, heavy light decomposition, usually again I am telling, we make use of it for the intense optimization or the extreme optimization. Just remember this one, right? So this is fine, man. Now yeah, next we will be discussing on the centroid decomposition. Now we have seen this one, heavy light decomposition. Next we will be going with a centroid decomposition, right? Just remember this one. We'll be going with a centroid decomposition next. So we are done with the heavy light decomposition algorithm. Let me summarize whatever we have learned so far. Just try to remember these 3 or 4 points, man. This is very important, right? So first thing here would be heavy light decomposition breaks the tree into logarithmic number of chains, right? So heavy light, this one, what do we call? Heavy light decomposition algorithm. So this one, heavy light decomposition algorithm, breaks the tree into logarithmic number of chains basically. Just remember this one. This is very important, right? So that's what we saw in the algo, right? So this is fine. Now each chain becomes segment in an array. Each chain, what it becomes segment in an array. Each chain becomes segment in an array. Just remember this one. This is very important. Enabling the segment tree queries. Enabling the segment tree queries, right? Segment tree queries. This is very important. This one point. Third one is time complexity. What would be the time complexity here? Basically, so building, so we went with a build function, right? So building would take big O of n, building the segment tree. So this one would take big O of n, and each query or the update, it takes big O of log square n. Just remember this. This is very important. So whenever we are giving contest in the CodeChef, this one, Codeforces CodeChef, or this one, whatever, this one, Etcoder, or if you are giving somewhere other than these platforms as well, if you are going with a CP, so many a times the last 2-3 problems might be it is based on the segment tree or the Fenwick tree, right? You can come across this one where you have to make use of this one, heavy light decomposition, right? So just remember this one. The time complexity would lead to big of n for the build, and this one for the query or the update, the time complexity would be big of log square n, right? So this is the time complexity for the build and query or the update. And basically when we make use of it, when we will be making use of the heavy light decomposition algorithm, so we will be making use of the heavy light decomposition for the problems like whether it may be path queries, whether it may be this one LCA based this one questions operations, sorry, LCA based operations as well, and updates on the tree prefix, and updates on the tree prefix, right? So these are some of the applications basically, right? So these are some of the applications. Again, heavy light decomposition breaks the tree into logarithmic number of chains. Each chain becomes the segment in the array, enabling the segment tree queries. And the time complexity we discussed building for the build, it's big of n. For the query or the update, it is big of log square n. And the final one would be this one. It is perfect for the problems like path queries, LCA based operations, and updates on the tree paths. So this part. So we are done with the finally we are done with the heavy light decomposition algorithm. Next, as I have said, we'll be going with the centroid decomposition. For now, this is it. Thanks for watching, guys.